Okay, so let's get started here. Um, so the problem reads, I have 4 identical pieces of candy. How many ways can I distribute them to Anne, Bob, and Catherine? So note that Anne, Bob, and Catherine are 3 distinguishable people, which means the 3 of them are different. So if I have 4 identical pieces of candy, and let's draw them here. 1, 2, 3, 4. So these 4 pieces of candy are all the same. So it doesn't matter what order we put them in. They do not necessarily each have to have at least 1 piece. So for example, Bob could have 0 candies, Anne could have 3, and Catherine could have 1. So the trick to doing these types of problems is ordering out 4 identical pieces of candy. And since you have 3 people, you're basically trying to make 2 cuts to these 4 pieces. So for example, if I made 1 cut here and 1 cut here, if the left segment always belongs to Anne, the middle segment always belongs to Bob, and the right segment always belongs to Catherine, then that means that Anne gets 1 piece, Bob gets 2 pieces, and Catherine gets 1 piece. So we've basically turned this problem into having 4 items and trying to arrange 2 sticks in such a way that they split the candies among 3 people. So can you guys try figuring out how to do that? Remember 2 weeks ago, we started learning about combinations. So the number of ways to choose k objects from a group of n is equal to n factorial over k factorial times n minus k factorial. Someone said 6 choose 2. That is correct. So how we get 6 choose 2 is we just picture. Let's switch a color. So let's picture we have 6 identical objects. So we have 1 thing here, 2, 3, 4, 5, 6. So out of these 6 objects, 4 of them are the candy, and 2 of them are the sticks we use to divide up the candy. So if we have 6 objects in total, and we have to choose 2 of these blue things to make sticks. So whatever pair we choose gets turned into sticks. For example, if I choose this and this, then that means these are turned into sticks. And that means that Anne gets 2 candies, Bob gets 0 candies, and Catherine gets 2 candies. Every single one of the 6 choose 2 equals 15 combinations of sticks and candies corresponds to exactly 1 arrangement of distribution of candies. So that's why the answer is 6 choose 2 equals 15. So let's move on to a slightly more complicated example. So this problem right here is the same exact type of question, except with slightly more difficult numbers. Someone asked for the last question, why is there 6? There's 6 because there's 4 candies and 2 sticks we use to divide the candies, and 4 plus 2 is 6. You don't necessarily have to determine which of the 6 objects are candies or sticks initially. 12 choose 3 is close, but the top number is not necessarily 12. 15 choose 3 is correct. So let me start explaining this problem here. So we have 12 identical pieces of candy. So we can picture, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sorry. 11, 12. Okay. So these are all our candies, and we want to distribute them among 4 people. Well, remember from the last time, if we want to distribute them among 4 people, we have to divide the candies 3 ways, right? So we need 3 dividers. And we can place these 3 dividers anywhere. So let's just say we choose 12 plus 3 objects. And out of those 12 plus 3, we choose 3 of them to be dividers. And that would equal 15 choose 3, which written on the board here is 455. So it's the same type of problem, except with slightly different numbers. So is everyone okay with that? Someone asked, why is 15 choose 3 455? Well, we learned that if we use the formula that we learned last week, then 15 choose 3 is equal to 15 factorial over 3 factorial times 15 minus 3 factorial. And then if you simplify this, it becomes 15 times 14 times 13 divided by 3 times 2 times 1. So if you calculate this, this will give you 455. Okay, so if we don't have any troubles with that, what I'm going to do is transition over to number theory now. So hang on one second. Okay, so here's our new topic, number theory. And this week we're going to be covering, and next week, we're going to be covering factors and divisibility. So we're going to be learning about primes, how to factorize numbers, divisibility rules, and a bunch of problems. So let's get started here. Our warm-up question is, which of the following numbers are prime? These 2 weeks might be a little light on course material because factors and divisibility isn't really a big topic, but let's just start here. The following numbers are prime. 2 is prime. 2 is the only even prime, actually. 3 is prime. 5 is prime. 7 is prime. And that's it. Some of you might be asking about 1. The number 1 here is not defined as prime and is not defined as composite. So it's the only number that is not either. A prime is defined as a number that is only divisible by 1 and itself with no other factors. Okay, so that was a pretty easy warm-up. Let's go into primes. So I just explained to you guys what a prime is, so you guys shouldn't have many questions about that. So let's say a number p is prime if only 1 and p divide p. So any other number besides 1 and p does not go into p evenly. And the composite number is basically the opposite of that. So a composite number is a number where there can be divisors other than 1 and p. So does everybody understand that? Someone asked, is there a fast way to determine if a number is prime? Well, later in the course, I think next week, we're going to be talking about divisibility rules, or even if we get to it this week. But if a number ends in, for example, an even number, then it's obviously divisible by 2. If a number, if the sum of the digits of a number add up to a multiple of 3, then it's obviously divisible by 3. So you can actually eliminate a lot of integers when you're checking for example, the first 30 primes. And as you work with primes more and more, you'll probably be able to memorize the first few. So you can probably get used to immediately identifying which ones are prime and which ones aren't. Okay, let's move on here. So here are some examples. Is 437 prime or composite? So to check if something is prime or composite, then you have to check if a number less than it can evenly go into it. And if there is no such number besides 1 and itself, then the number is prime. Okay, so the answer here is composite. 437 is actually 19 times 23. There basically was no quick way to do this. There is no magic formula, but there are a few tricks you can use. So for example, to check if something is prime or not, all you have to do is check that number divided by any prime number. So for example, 2, 3, 5, 7, 11, 13, and so on. If you check these numbers one by one, then you'll check if the number is prime or not. Okay, so let's move on. Is 1001 prime or composite? So 1001 is actually a number that a lot of math competitions like to use. So you should probably memorize the prime factorization of this. Okay, so the answer is composite. 1001 is actually 7 times 11 times 13. So if nobody has any questions, we'll move on to the next problem. Is 727 prime or composite? For those of you choosing composite, can you tell me in the chat exactly what its prime factors are? Okay, now everybody is saying prime. And you are right, this is prime. So for example, if you wanted to write the prime factorization of this, the only thing you could write is 727 equals 1 times 727. Okay, now we are going to be talking about factorizations. So how do you factorize a number? So factorization is basically breaking a number into a product of its prime components. So if I gave you the number 100, for example, writing 10 times 10 is not a proper prime factorization. You have to break everything down to a prime number. So 10 you can break down into 2 and 5. So it's 2 times 5 times 2 times 5. And then you could rewrite this as 2 squared times 5 squared. This would be a proper factorization. And this is not. So how do you count factors? Well, you could start by listing them out. Can anyone list all the factors of 100? 1, 2, 4, 5. Yes. 10. 20. Yes. 25, 50, 100. I think we got all of them. So the way you count this is you have to remember back to number theory. Counting. So this 2 squared here means that there's a total of 2 2's that we can use. So whatever factor of 100 we get has to either have 0 2's, 1 2. Hang on, let me write it a different way. 0 2's, 1 2, or 2 2's. And we physically cannot go above 2 2's because if we try 3 2's, then it wouldn't be a factor because 3 2's is bigger than 2 2's. So similarly for 5's, we can have either 1 5, 2 5's, and then of course 0 5's. So there's only 3 options you can have here and 3 options you can have there. So can anyone tell me a simple way we can use to count the number of factors of 100? Remember that we cannot have 0 2's and, for example, 2 2's at the same time. We have to choose one of them. Okay, someone said 3 times 3 is 9, and that is correct. So we consider prime factorizations by the prime. So we have 2 individual primes here. 2 is a prime, and 5 is a prime. So for 2, we can either have 0 2's, 1 2, or 2 2's, so that's 3 options. And regardless of what we choose for the number of 2's, we can choose 1 5, 2 5's, or 0 5's. And that's another 3 possible combinations. So since these two are independent, we can multiply them, and that gives us 9. And a simple trick to do this would be noticing that 9 is also equal to the exponent of the first prime plus 1 times the exponent of the second prime plus 1. And so that's a quick way to count the number of factors of a number. Okay, so let's go over LCMs and GCDs. So basically, an LCM is a least common multiple, and a GCD is a greatest common divisor. So for example, if I had two numbers A and B, then the LCM of A and B, and in math notation, it's usually written this way, is the least common multiple of A and B. So let's call that K, a number K. So the number K, the least common multiple, has the property that K is equal to a multiple of B and a multiple of A, which means that you can multiply A and B by some integer to get K. And the least part means that this K is the smallest possible. So for example, if I gave you two numbers, let's say, what is the least common multiple? Hang on, let me erase some stuff. So what's the least common multiple of 4 and 6? Okay, good. A lot of people are saying 12. Be careful, it's not 24. Because you might think it's 24 because 24 is obviously a multiple of 6 and obviously a multiple of 4. I mean, it's 4 times 6, right? Well, there's a least part in least common multiple. 24 is a common multiple, but it's not the least one. The least one would be 12. An easy way to determine the least common multiple is to look at the number's prime factorizations. So the prime factorization of the number 4 is equal to 2 squared. And 6 is equal to 2 times 3. So what we would do here is we would actually compare prime factors. 4 and 6 both have a prime factor of 2. 4 has 2 2's in it. 6 has only 1 2. And when you're considering LCM, you always pick the one with the greatest number of a prime factor. So in this case, we would pick 2 squared over 2. Now for 3, we notice that 4 equals 2 squared, but that can also be written as 2 squared times 3 to the 0, because 3 to the 0 is just 1. We can multiply by however many ones we want. And here we have 3 to the first power. And since there's 1 3 here and there's 0 3's here, we always pick the one with the more 3's. And so 2 squared times 3 to the first is equal to 12. So this is the real least common multiple of 4 and 6. So did everybody understand that? Okay, good. So now we're going to go over GCDs. So a GCD is a greatest common divisor. So that would be the greatest number that is a divisor of both A and B. And the notation is usually written this way, with the letters GCD. So let me give you guys an example. Can you find the greatest common divisor of the example I just gave you, 4 and 6? Okay, so a lot of you have correct answers. Good. Okay, so the way we do this is we start off the same way. 4 is equal to 2 squared. 6 is equal to 2 times 3. And we can add an invisible 3 times 3 to the 0 here. So what we do here is in LCM, we consider the greatest number of primes for each category. But here we're going to choose the least. So 6 has less 2's and 4 has less 3's. So therefore the GCD is equal to 2 to the 1 times 3 to the 0, which is equal to 2. Okay, so are there any questions? Why is it not 1? 1 is actually a divisor. 1 is a divisor of every single number, but it's not the greatest one. So just like with common multiples, there's a least. With common divisors, there's a greatest. 2 is the greatest common divisor, which means there's no number above 2 that would evenly go into both 4 and 6. Yeah, that would be LCD. And that's kind of useless because the LCD is always 1. And yes, it can be called GCF too. And someone also asked if there was going to be a Q&A session. There is not. We used to have a Q&A session a few weeks ago with Benjamin, but there wasn't enough demand for that. So you can feel free to ask questions here and I'll answer them. So before we end class, let's do some problems. Factorize the number 225. Okay, so let's start this. So 225. Well, the first thing you might do if you see an unfamiliar number is to try to see what goes into it. Well, we haven't learned divisibility rules yet, but I'm going to tell you right now that 225 ends in a 5. And if something ends in a 5, then it's divisible by 5. So if we divide 5 into it, we get 5 times 45. And 45 ends in 5 again, so we can divide another 5 out. So that becomes 5 squared times 3 squared. And that is our factorization. Someone asked if you can divide by 3. It doesn't matter what order you divide, as long as you get 3 squared times 5 squared at the end of it. So yes, you could. Someone asked, what does the exclamation point stand for? I am not sure what you mean by that. Well, yes, factorial is that. Were you referring to the, oh, you were referring to the stars and bars thing? In number theory, you don't really use factorials. Well, let me just quickly explain. So a factorial is, n factorial is defined as n times n minus 1 times n minus 2 all the way down to 1. Well, why do factorials end with an exclamation point? Well, that was how it was defined. So you can ask like some mathematicians about that. Okay, so next problem. How many factors does the number 420 have? Okay, so let me just quickly go over this problem since we don't have that much time left. 420. In divisibility rules, you learned that anything that ends in a 0 actually has a factor of 10, and 10 can be written as 2 times 5. So 42 ends in a 2. Well, you could do this several ways, but let's just say for now it ends in 2, so you can take a 2 out. 2 squared times 5 times 21. 21 is 3 times 7, so that is equal to 2 squared times 3 times 5 times 7. I forgot. This question wasn't asking about that. This question was asking about the number of factors. Well, we learned from before that the number of factors is all the exponents added 1 and then multiplied together. So the exponent here is 2, and these three exponents are 1. So 2 plus 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 equals 3 times 2 cubed, which is equal to 24. Okay, so before we go, I just want to mention that we actually have a YouTube channel now, and this class recording will be posted on it later. So I'll be posting more about that in Classroom. So see you guys, and we're going to be ending this lesson. The name of the YouTube channel is Alphademic Learning. So if you search for that on YouTube, you can find all of our videos. Okay, bye guys.